let's begin. Let's start our seminar. And I suggest to divide our seminar on two parts. And the first part repeat some problem which devoted to quadratic surfaces. On the last seminar, we began consider to such problem, and to solve maybe 2 or 3 such problem. But in my opinion, enough important to understand how to solve the following simple task: determine type of the surface. We have some canonical equation for the surface, but in this case we have quadratic term and linear term, and the idea to reduce such form to the canonical form. We can to group the element which contain the same variables, quadratic and linear term, and simplify to using the formula for the square of the sum. In this formula, the product of various unknown are absent, and in this case we can use most simple simplification of such formulas, which simplification used only some simple formula. For example, let's simplify the first formula. Let's group the term contains variable x to x square minus 4x plus y square plus 4y minus 3z square plus 6 is equal. The first two terms we can rewrite in the following form: 2 multiply x minus 1 square. Easy to see that this term is equal x square minus 2 square plus 1, which we multiply on 2. And these terms coincide with the terms in the initial expression, and we obtain complementary constant term 2 multiply 1, and we must subtract this term, and after this we obtain that this expression is equal to the sum of the two first terms in the initial expression. The same way we obtain the equivalent expression for the following two terms: y square plus 4 times y, y plus 2 square is equal y square plus 2 times 4 times y plus 4. We subtract 4 minus 3z square plus 6, and the final form is equal to x minus 1 square plus y plus 2 square minus minus 3 z square is equal 0. And we obtain some expression. What the surface we obtain? Or this surface. We can use the new reference system x square x minus 1, y square y plus 2, and we can rewrite this equation in the following form: 2x prime square plus y prime square minus 3 z prime is equal z. Z prime square is equal 0. What's the equation we obtain? What the quadratic surfaces is obtained by this equation? Easy to see that we obtain the cone. I recall that canonical form of the cone. How to reduce this form to this? We can obtain, for example, we can obtain or multiply the, I'm sorry, excuse me, is equal 0. We can divide it or multiply on the arbitrary non-zero numbers, and this equation we can write in the. Let's divide it. Let's divide this equation, the left hand of this equality, for example, on the 6, and we obtain the full expression. Is to see that this equation is exactly the equation of the cone, and the sizes of the basic parallelepiped is equal root square 3, root square 6, root square 2. If the right side is some positive number, in this case we obtained the simple hyperboloid. double hyperboloid. Ellipsoid and two type of paraboloid. Elliptic and hyperbolic. Hyperbolic. And I try to draw this cone. Maybe such. Cone. In this case, a is equal root square 3, b is equal root square 6, c is equal root square 2, and this coordinate system is shifted. The new coordinate system x prime is equal x minus 1, y is equal y minus 2. I'm sorry. Y plus 2 x x y plus 2, I'm sorry, x minus 1. Z x y y prime x prime z prime. The draw of this column. Many maybe question? Any question? Do you understand how to? Okay, yes. Let's continue. The second equation is the same, but in this case we can shift the quadratic part is the same as the previous case, but the linear part is equal 6 times z. We have the same transformation in this case, but we must group these two terms, and in this case we obtain minus 3 z.
In this question, in the right part, we wrote 2x prime to the power of 2 is y prime square minus 3z prime square. And what number did you divide it by if you get square root of 3?
Yes, this.
What did you divide this number by?
This expression. Do you ask this transformation? Yes.
Yes.
We have the in the right hand the 0, and if we multiply left and right side on any numbers, we obtain the equivalent equation, because 0 multiplied other term is equivalent, and we can multiply or divide it on any term, and yes,
24.
I'm sorry. I'm sorry.
No, it's okay. I thought, yeah.
No.
You divided by 6, I think.
No. Yes, I divided 6, but maybe you're right. This expression uniquely defined from multiplication of non-zero element, and we have the other. We can rewrite this in the following form. And it will be equivalent form. We can also rewrite, I'm sorry, this expression in such form. And this form and this form are equivalent, because this equation we can multiply on other numbers. If we fixed some value for z, we obtain uniquely defined section of this surface, and this section uniquely defined up to proportional constant term, and this numbers is not uniquely defined. We can multiply each of them by to any non-zero constant, and after them we obtain the equivalent equation. This term is not uniquely defined for cone, but if in right hand non-zero term, this constant uniquely defined, and in this case we obtain the following expression: this z square minus 2z plus 1, and we must obtain, we must obtain 3 is equal 0, and in this case we obtain uniquely defined equation for the c times z minus 1 square is equal minus 3, and we obtain x square divided and in this case we obtain uniquely defined values for parameters in this equation. A is equal root square c divided 2, b is equal root square 3, c is equal 1, and we obtain equation for double paraboloid. We can see that in the case 1 and 2 we have from the first point of view the same equation. We have the same quadratic term, and the difference only the linear term, but the surfaces which define this equation are different. In the first case we obtain cone, and the second case we obtain double hyperboloid, shifted hyperboloid, and shift. Zero. Shifted hyperboloid. this cone, if we shift, will be asymptotic cone for this hyperboloid after the same shift in the direction x, y, and shifted in direction of z. And these two quadratic surfaces connected one other, but this relation is not simple. It's not simple. Maybe any question? This most simple problem. Yes, it's enough. Enough understand. Okay, let's finish the first part and move to the second part, which devoted Gaussian elimination method. And I suggest to consider some example solution of linear system. We will use naive point of view. We will use naive variant of elimination method. First of all, let's consider the augmented matrix of some linear system. And we can see that we have three columns which has the following property. In each of these columns exists only one non-zero element, and this non-zero element is equal exactly 1. And this column is 3. In the second column, 1 takes place lies on the second rows. In these columns, on the first rows, and in these on the third rows. And we can see that one of the properties from definition of reduced echelon form is also fulfilled. And in this case, we obtain the row echelon form. And we can write solution of this equation. Reduced row echelon form is equivalent to solution. And this matrix is defined the solution. This matrix is exactly a solution of system. The solution coincides with this matrix. We can just write the solution of the system in the following form. x1 is equal. We shift the other term in the right side and change the sign. In the first row, on the second place, lies coefficient 6. It means that these coefficients in variable x2 after shifted after we shift this term in the right side, we obtain the term minus 6 times x2. We change the sign. We obtain x1 is equal minus 6 x2 minus 4 x4 minus 2. We write first row as equation and transfer the other variables, included first variables, in right side. And second row, x2 is equal. We have independent variables x4 with non-zero coefficients, and after when we shift this variable in the right side, we obtain minus 3x4 plus 1. The third column, x3 is equal minus 5x4 plus 2. We divided our variables x1, x2, x3, x4. I'm sorry, my mistake. x1, x2, x3, x4, x5. I'm sorry, mistake. x5, x5, x4. I'm sorry. We have 5 variables, x1, x2, x3, x4, x5. And we divided these variables onto parts. Independent variables and dependent variables. And independent variables expressed in the terms dependent variables. This exact expression for this relation between these variables. We can put the independent variables equal arbitrary values. For example, x2 is equal 0, x5 is equal 0. And from this formula we obtain that in this case x1 is equal minus 2, x3 is equal 1, x4 is equal 2. And we obtain a so-called partial solution. I put x2 and x5 is equal 0. And in this case, I obtain that x1 is equal minus 2, x3 is equal 1, x4 is equal 2. If, for example, x2 is equal 1, x5 is equal 0. In this case, we obtain x1 is equal minus 6 minus 2 is equal minus 8. In these cases, I obtain 1, 2. And I obtain other solution. In such way, we can obtain any solution of any partial solution of this equation, and this expression is exactly general solution of our linear system. And we can see that reduced row echelon form is equivalent. The general solution of linear system is equivalent to general solution. Any question? Do you understand that? This first fact. And our goal to obtain this form of augmented matrix. And after them, we can obtain the general solution of this equation in such form. And if we have general solution from this general formula, we easy to obtain partial solution on the following way. We can put the independent variables for arbitrary values. I put arbitrary numbers in this case. For example, I can introduce some parameters. For example, u and v. I have the following variables: x1, x2, x3, x4, x5. And I have independent variables x2 and x5. And I can put x2 is equal u, some parameters, x5 is equal v, other parameters. And I obtain exact expression, all variables, all unknown, in terms of these parameters. X1 is equal, x4 is x5. Instead, minus 6x2 minus 4x5, and minus 6u minus 4v minus 2. x3 is equal minus 3v plus 1. x4 is equal minus 5v plus 2. And I obtain parametric form for our solution. Do you understand? Any question?
It's okay.
Mm-hmm. Yes. The first step, we consider a relation between reduced echelon form and various form of solution of a linear system. And our goal to obtain this form. After them, we can easy to obtain the general solution in the various forms. And these forms are equivalent. The first form, when we express dependent variables in terms independent, and second form, so-called parametric form, when we use some parameters for expression our variable. In this second case, we can use a geometrical interpretation of our solution. The variables, we can consider the unknown of the variables x1, x2, x3, x4, x5 as the coordinates of the point in the many-dimensional space. In our case, we have 5-dimensional space, and we have two parameters, u and v. And this parametric form can be, we can consider this parametric form of solution as a way to map the plane. We have two independent variables, u and v, and this independent variable can be considered as a point the some standard coordinate plane, u and v, and we maps the standard coordinate plane into 5-dimensional space, and these formulas define this mapping which maps coordinate plane in many-dimensional space, and the image is a plane in many-dimensional space. This each equation is a hyperplane in 5-dimensional space. This every equation defined the 4-dimensional hyperspace in 5-dimensional space, and we have three 4-dimensional space, and this space intersect. Its intersection is a 2-dimensional plane. For the second two, the dimension of 1, 4, when we intersect another, we define 3, and intersect the third, we obtain the dimension 4. We obtain 3 plane in general position, and reduce echelon form corresponds each rows of reduced echelon form corresponds to the some hyperplane, and we obtain some collection of hyperplane in the general position, in reduced echelon form. Okay. The second step, let's to solve one of the linear system, and our solution will be used reducing to the echelon form augmented matrix of this linear system. First of all, let's write the augmented matrix of our linear system. The columns of augmented matrix, the first column is a coefficient is formed by coefficients in first variable in our linear system. The first column, in our case, 2, 3, 8. 2, 3, 8. The second, -1, 3, 5. 3, -1, 1. And constant column, constant matrix, the numbers which lies in the right hand of our equation from our linear system is 3, 8, 60. And the main idea to eliminate some variables from equation number 2 and number 3. Let's exclude the variable x1. We have the x1, x2, x3. We have 3 variables. And first step, we can suggest these variables. We can use the elementary transformation. How to exclude variable x1 from third equation? Easy to see. If we subtract from third equation the first which multiply on 4, we obtain the 0, and we exclude this term. In the second case, we can subtract from second equation first, which multiply on ratio 3 on 2. And we also obtain, as a result, elimination of this variable from the second equation. But in this case, we obtain the non-integer numbers. And to work with non-integer numbers and more hard than the integer. And we can use complementary transformation. We can obtain the first element which such that this element divided the other element of the first row. In our case, we can easily to obtain this. We obtain the such equations, the such rows, which has the first element which is equal 1. We can subtract, for example, for the second row first. Row 2 is equal row 2 plus minus 1 multiply R1. The goal of this transformation obtain this the first element in some rows which is equal 1. After this transformation, the first and third rows are not changed. 1, 4, minus 4, 5. Let's change position of first and second rows. Our goal to get this element, to transform this element to 0. We can subtract from third rows second, which multiply on 4. R3 is equal R3 plus minus 4 R2. Second rows is not changed. First is not changed. The third rows is changed. Multiply to minus 4 plus, minus 8 plus 8 is equal 0. Multiply minus 4 on minus 1, 4 plus 5 is equal 9. Multiply 3 times minus 4, minus 12 plus 1, minus 11. Minus 12 plus 16 plus 4. Plus 4. Eliminate the first variable from the second equation, from second rows. R2, we will put the difference R2 plus minus 2 R1. We want to obtain this element is equal 0. One times minus 2 is equal minus 2 plus 2 is equal 0. Minus 8 minus 1 minus 9. Minus plus 8 plus 3 is equal 11. Minus 10 minus 10 plus 3 minus 7 minus 10 plus 3 minus 7. Okay, and last step, to add to the third row second R3 plus R2, and we obtain the following. What does it mean, the final matrix? We can see that last row is in ostrich form on the left side. we have 0, but in right side we have -3. It means that we obtain the equation in the following form: 0 times x1 plus 0 times x2 plus 0 times x3 is equal -3. What does it mean, this equation? Easy to see that this equation has no solution. On the lecture, I consider the same example. If we put the unknowns arbitrary values, any arbitrary values, in the left side, in the left hand of this equation, we obtain 0, only 0. But in the right side, we have non-zero element. And we obtain contradictory. The left hand is not equal right for any values. It means that the set of solution of such equation is empty. And our linear system also has no solutions. In this example, the set of solutions is empty. No solutions. It does mean that in three-dimensional space, this plane are not have no general point. Have no general point of intersection. Any question?
Thank you.
In this case, and we consider the case of row echelon form which has no solutions. We can conclude that the matrix of coefficients have only two non-zero rows in reduced echelon form, but augmented matrix has three non-zero rows, and the number of non-zero rows of matrix of linear system is less than number of non-zero rows of augmented matrix. And in this case, the linear system has no solution.
So if all the values, for example, x1, x2, x3, the sum of them will be 0, then it will have no solution?
Yeah. This general property of reduced echelon form, because in this case exist rows which element which lies on matrix which are coefficients of linear equation all equal 0, but constant term is not equal 0, and this linear equation is contradictory. Such linear equation has no solutions. We can put the variables of any values, any arbitrary values, but in the left side, in any cases, we obtain 0. But in the right hand, we have non-zero element. 0 is not equal to non-zero. And this contradictory equation has empty set of solution. But solution of linear system is intersection of solution of the solutions of linear system which consist of this linear system. And if we have empty set, the intersection with empty set, any set is empty. And in this case, we obtain the empty set of solution. And property of row echelon form is following: the sufficiently condition for the case when the set of solution is empty. The number of non-zero rows in the matrix of echelon form is less than number of non-zero rows in the augmented matrix. In the matrix, in this case, in the matrix we have 2 non-zero rows, but in the augmented matrix we have 3 non-zero rows. 2 less than 3. And this general condition. If the numbers of rows we will call the rows of echelon form of matrix A by rank of the matrix A. And the numbers of non-zero rows in the augmented matrix of linear system we will call rank of augmented matrix. If rank matrix less than rank augmented matrix, the set of solution is empty. Later we prove this theorem, which this theorem is called Kronecker-Capelle theorem, and we define rank of arbitrary matrix. Strictly speaking, the rank of arbitrary matrix have numbers, the number of non-zero rows in the echelon form, in the reduced echelon form on this matrix. And later we strictly prove that this definition is correct. If we have matrix, we can obtain various reduced echelon form of this matrix, but the numbers of non-zero rows in this various echelon form are equal. And we obtain the correct definition of the rank of the matrix. Okay, let's consider the following example: linear system. rewrite this linear system in the matrix form. The augmented matrix of this system is following: the first column 1, 2, 3, the second 2, 5, 10, 3, 6, 9, 4, 8, 12, 3. Okay. We have the following transformation. We want to obtain on this place the 0 element and this place 0 element. You can use the first type elementary transformation, and first elementary transformation, let's put R3 is equal R3 plus minus 3 R1, R2 is equal R2 plus minus 2 R1. In this case, we can see that the first element of the first column divides the other element of this column, and our transformation can be easily calculated. We have the first rows. The last rows has a following form: minus 3 times 1, minus 3 plus 3, 0, minus 6 plus 10, 4, minus 9 plus 9 is equal 0, minus 12 plus 12, 0, minus 9 plus 13 is equal 4, minus 2 plus 2 is equal 0, minus 4 plus 5 is equal 1, minus 6 plus 6 is equal 0, 0, 1. We can multiply the last rows on ratio 1, 4. And we obtain the same rows. And let's subtract from the last row second. And we obtain 0 rows. The last step, the second column. In the second column we have on the second place 1, and on this place we have 2, and we want to obtain on this place 0, and let's subtract from the first row second. We obtain I'm sorry, minus 2 R2. If we want obtain on this place 0, minus 2 plus 2 0, 3 4 1, and we obtain the echelon form. The first two variables are dependent, and we obtain the solution in the following form. x1 is equal minus 3 x3 minus 4 x4 plus 1. X2 is equal 1. X2 is equal 1. Easy to see that we obtain that set of solution is a plane in a four-dimensional space. In the parametric form, the solution has the following parametric form. Let's put x3 is equal the first parameter u, x4 is equal other parameter v. x2 is equal 1 is constant. This variable is constant, and x1 is equal 3 times u minus 4 times v plus 1. And we obtain the expression of all unknowns in terms of the two parameters u and v. And in this way, we can obtain various partial solution. We can put u and v the various values and obtain the corresponding values from variables of solutions. But infinitely many solutions. Any question? Okay, let's consider one more example. In my opinion, enough interesting example. If the constant term in the linear system is equal 0, such linear system is called homogeneous linear system. Homogeneous linear system. And in this case, the solutions of such homogeneous linear system has the important property. The solutions form a vector space. Easy to see that n tuples of numbers form the n-dimensional arithmetical vector space. And the first semester we discussed such example. And solutions from this point of view, solutions of linear system are element of this vector space. And we can consider this n tuples as arithmetical vectors. And linear equation, some condition. Easy to see if we have two element x0 1 x0 n and x till x1 x and 1. We have two fixed vectors of our space, and let's suggest that these numbers are solutions of our equation. Easy to see that the sum of these vectors, the sum is the vectors which has the coordinates x1 0 plus x1 1, x1 0 plus x1 1. In this case, this vectors is the solution of our linear system. Easy to see, we obtain the following expression. This expression is equal 0 because the n-tuples x1 0 xn 0 is a solution of this equation. Then the sum is equal 0. The second sum is also equal 0 because the second n-tuple x1 1 xn 1 is also solution. And we obtain that 0 plus 0 is equal 0. If we obtain one of the solution on lambda, we also obtain solution. If we first solution multiply on lambda and to add a second solution, we obtain such n-tuple. And if we substitute the tuple in our linear equation, we obtain the following equality. And easy to see that in this case we also obtain lambda times 0 plus 0 is equal 0. And this combination is solution, is also solution. It means that the combination of solution of linear equation is also solution, is linear combination. If we have more than one equation, if we have linear system of linear equation, in this case we have the same reasoning. This reasoning is true for any equation of linear system. Therefore, this reasoning is true for linear system. So the set of solution of linear system form vector subspace of our space. It means that any linear combination of solution is also solution of our system. It's enough convenient property to work with such linear system, and we will use this observation. And how we can use this observation? If we have vector space or subspace of vector space, and in this space we can consider so-called linear independent system. Linear independent system has the following important property. Any element of this system cannot be expressed in terms of other element. And if we have so-called maximal independent system in vector space, which maximal independent system is called basis. The basis has two basic properties, the main properties. First of these properties, any element of vector space can be expressed as a linear combination of vector of basis. And the second property, this expression is unique. And in this case, we can obtain the simple way to describe the solutions of the linear homogeneous system. We can find basis in the space of solution, and this basis uniquely defined all solution of linear homogeneous system. It's pity I have no time to continue, but on the next lecture we will look for basis. Thank you.